Hi folks, in this video we are going to cover section 3.7, inverse functions. Let's start with our warm-up. The warm-up looks like a composition which we covered previously. So I'm going to find f of g of x first. So I'm going to plug in my g of x equation to my f of x equation. So here we go. I'm going to end up with x. And then I'll do the other one in blue. So I'm going to plug in f of x into g of x. Okay, that also gives me an x. That means, which we're going to talk about later today, that these are inverses of each other. Okay. The same thing is going to happen for b, so I'm just going to go ahead and skip it and move into what inverses are. Okay. We write them, first of all, as f to the power of -1. Okay, this is not actually a power. It's just how we represent an inverse function. Okay, it's inverse f inverse of x. That's how we read that. It is not a negative exponent. It does not imply a power of -1. That's really, really important. It is simply the notation. Something else that's really important about inverses is that the function and its inverse switch their x and y values and their domain and range. So something that is really useful to remember is that for the function, the x value and the y value and the domain and the range flip-flop. So for the inverse, we essentially write the opposite. Okay, so here's the domain, the range, and the coordinates for both. Okay, they are going to flip-flop. So the y value becomes the first value, the x value becomes the y value. Okay, so for example, if I had 3, 5, this would become 5, 3. Okay, x comma y flips, and our new x value is 5, our new y value is 3. Okay, the domain becomes the range becomes the domain. Okay. When a function has no inverse, it is possible to create a new function and it might exist on a limited domain. That happens with a quadratic, so keeping in mind that negative roots don't exist, which is why this part of the function is missing over here, okay? It doesn't exist on a negative y value because negative roots aren't graphable, right? They're imaginary numbers. And so roots are an example of where there is a limitation to what we can graph or what we can solve for, okay? Now, mathematically, there's several steps to finding the inverse of a function. There are 5 of them. Only one of them is math. So here is your math step, okay? The first one is to make sure it's a one-to-one. If it's not one-to-one, it's going to have a restriction just like the root function. So I'll just draw an arrow up there to kind of remind you that there is a restriction if it's not one-to-one. Then step 2, switch f of x with y, then switch x and y, then solve for y, and then finally write f inverse of x instead of y, so using that correct notation. So let's go ahead and do that with the first example. We're going to go ahead and write y equals 2x plus 2. Then we'll switch x and y. Now I'm going to go ahead and solve. Okay. I'll simplify this as x over 2 minus 1. And that will be f inverse of x equals 1/2 x minus 1. So that's going to be my inverse function, okay? I am going to go ahead and plot that. I'll plot both. So we'll do the original in red at 2, rise 2, run 1. Our line's going to be here. And then my other line will start at -1, go up 1 over 2, up 1 over 2. Okay. Something that you will notice is that the coordinates kind of flip-flop. So for example, this, I'll write it in black, is 0, 2, and this point is 2, 0. So just because you graphed one of them, you can graph the other one by simply switching your points, okay? That works every single time. Notice that this dashed line is what they are reflecting over, okay? That is the y equals x line. Whoops, meant to do that in yellow. Okay, it's not quite even. Move that down slightly. Okay, it's called the identity function. Every single inverse is going to reflect over the identity function. It is y equals x. So when x is 1, y is 1. When x is 5, y is 5, and so forth. Okay? Let's do the next one. Now we have a quadratic. Notice that it already tells you your restriction is going to be x is greater than or equal to 0. So I know for my quadratic, it will exist, but for my inverse, it will not. I can make a table of values for my quadratic. So I am going to pick a negative number because I do know that it's going to exist for my quadratic. So that'll be -1 squared plus 2, 0 squared plus 2, 1 squared plus 2, and 2 squared plus 2. Okay, that'll get me 3, 2, 3, and 6. I'll go ahead and plot those points. I'll make that blue. So -1, 3, 0, 2, and then 2, 6. I'll know it'll mirror on the other side. All right. So now for the inverse one, I'm really only going to work with those positive values. And I'll go ahead and plot those in reverse. So 2, 0, oops, yeah, 3, 1, and 6, 2. Okay. There is my inverse function, keeping in mind the dashed one theoretically does no longer exist. So here is the inverse, and here is the original. Okay, let's do this last graph here. I will graph the original in purple. We can again make a table of values. So I will just go ahead and plug in some different points. I'm going to pick strategic points so that I know that it's graphable. But theoretically, I would have tried -1, 0, and 1. So let's do that for all of these. -5 plus 3 cubed, -3 plus 3 cubed, -1 plus 3 cubed, 0 plus 3 cubed, 1 plus 3 cubed. So we're about to see why 0 and 1 aren't exactly going to be convenient for us to graph. So I'm going to end up with -8, and then 0, 8, 0 plus 3 cubed will be 27, and then 4 cubed will be 64. Those are much too large to graph, so that's why I theoretically I strategically chose -5, -3, -1. I knew that those were going to work, right? You might not have known that, and that's okay. This is kind of a trial by error, or if you have a graphing calculator, use it to your advantage. Okay. So let's go ahead and plot those points. I'll be at -5, -8. -3, 0, and -1, 8. Okay. So my curve is quite elongated here. So I'll do my best to draw that. So that's going to be f of x. Now, if I want to draw the inverse, I can simply just flip those numbers. So my inverse would be 8, -1, and 0, -3, and -8, -5. So here's a point, here's a point, and here is a point. And so that curve looks like this. Okay. Now, algebraically, we could have also solved this. So algebraically, I could say x equals y plus 3 cubed, take a cube root of x, and then subtract the 3. And my inverse function would be the cube root of x minus 3. That does match my green curve. Just in case you're curious, go ahead and graph in a graphing calculator and you'll see that those line up. All right, let's take a look at using the table. Essentially what this is telling you when you have inverses versus a regular function is the x the input or the y the input? Here we're saying x is equal to 1 and y equals what? Because we're basing this off of the original function. So when x is 1, we get 0. Here we're saying the output of the original function was a 9, which means we're looking at this and we're getting 8 as the original input, right? But with inverses, we're saying 9 goes in, 8 comes out because x and y have flip-flopped. So in this one, we say when x is 3, we get 4. And here we're saying when the output was 4, we get a 7. So notice that they are just flip-flopping. All right, folks, that covers it for this section of inverse